So this lesson is on 6.1, estimating finite sums. So what this is saying is that before the days of calculus, what mathematicians did was they take the area between the curve and the function, and they actually use rectangles to approximate the area, right? So the way to draw the rectangles, there's actually 3 ways to draw the rectangles. As you can see the notes here, there's a left rectangular approximation method, there's a right rectangular approximation method, and there's the midpoint rectangular approximation method. So in short, we call them LRAM, RRAM, and MRAM. Now, these are approximations, so really keep in mind these are approximations. They're not going to give you the exact answers, but of course this is pre-calculus days. So with calculus, what it allows us to do is it actually will allow us to find the exact answer between the curve and the x-axis, that area that we're looking for, right? So right now we're looking at how these approximations work. How do we draw rectangles to help us get an idea of what the area should be, right? So first things first, you want to define what does it mean? What's the difference between left rectangular approximation method? Sorry, from this point on, I'm going to call it LRAM because it's just a lot of words. So what's the difference between all these RAMs, right? What are the differences between LRAM, RRAM, MRAM, all these rectangular approximation methods? So let's talk about the first one. So the left approximation method, by our definition, or I mean in our ways of describing it, is to, let me see if I can get this correct so that it doesn't take up too much room. So how do you do it? You use, all right, I'm going to type this out. Use endpoints on the left side, and you're going to draw towards the right, right to complete your rectangle. All right. And so again, if you were to look at a graph, this is how you would do it. And if you were to look at just the t-table, because sometimes we don't really have a graph to look at, which we'll talk about later. So if you don't have a graph to look at, then the other method that you're looking at is you're going to use all the y values. Sorry about this. Where am I? Y. Oh. Okay. All the y values. There you go. Values. Oops, not values. Values. Or f of x values. You're going to use all f of x values except the last one. Okay. All right. So I'm going to shrink this down a little bit so I can fit in this space. All right. Beautiful. And of course, if I'm talking too fast or this is just too much for you to write down in this short time, I would recommend that you pause the video and make sure you can get all of this down. Okay, so that is for LRAM. So then, of course, you can probably guess what RRAM is going to be. Since LRAM uses the left side, we're going to use right side for RRAM. So for me, there's a reason why I'm color coding this, so just bear with me, all right? So that's why this is going to take me a little bit longer than I want to, but this is going to be helpful in the long run. Trust me on that. Okay, let me get this over the right way. Okay, so you're going to use, all right, this one you use the endpoints on the right-hand side. On the right side, draw towards the left to complete the rectangle. And then of course, if you're looking at t-table wise, then this is using all the y values or f of x except the first one. Okay, beautiful. All right, so again, main difference between those two, one is using the endpoints on the left-hand side, one is using the endpoints on the right-hand side. So then you probably can guess what midpoint is. Midpoint is neither left nor right. You want to use the middle between the left and the right, right? So you want to use the midpoint, all right? So let's get my rectangle here a little bit better, and that way I have enough room. Okay, almost there. Okay, so this one you're going to use the midpoint, find the height of the rectangle. Then you're going to complete the rectangle using that height. And again, I'll show you through the example, right? And unfortunately, then your t-table, you actually have to create a new t-table using these midpoint values and find new y values to use, right? So you'll need to create a new t-table using the midpoints of the x values. Okay, all right, so now we're going to take a look at how that's going to work out in terms of these three different ways, right? So we're going to approximate the area under the function in the specific domain. So here is our function. It's not a very pretty one, and in fact I chose something that's kind of gross so you can see a little bit more of what the graph looks like. All right, so in the interest of making sure we have enough time and enough room to do this, here's what I'm going to ask you to do. I'm going to ask you to take a few moments here to just mark up your x and y axes. You want to make sure your x-axis is a little bit wider because you're looking at here, you're looking at -2 to 1. So you're really not looking at a huge area here in terms of the x values. So I would suggest you make every 4 box 1 on the bottom. So here is 1, 2, so -2, and here's 1, 2, +2. For your y values, you want to make every other box is 1. So you go 1, 2, 3, 4. Maybe at the end of the arrow, that's 5. All right, not y, 5. All right. So you're going to do that for all 3 pictures because it's the same exact graph over and over again, except we're using different approximation method to show you what values each approximation gives you and which one is the best. Because yes, there is an approximation that will get you the closest depending on the shape of your graph and depending on the concavity as well. All right. So here you have 1, 2, -2, 1, 2, 3, 4, 5. And then you get 1, 2. Okay, you can get this graph really nicely by filling out a t-table for this, right? So our domain is -2 to 1, and it says n equals 6. That means we're going to take from the region from -2 to 1 and divide it into 6 rectangles, right? So that actually helps us make our t-table. How do I make my t-table? Well, I know I'm going to start at -2. I'm going to end at 1. And I am going, oh, actually, sorry for this, because I'm trying to color code this. So I'll make sure I'm using something that is not going to confuse you with the rest of the rectangles. Okay, one more time. So I'm going to start with -2, end at 1. And because of n equals 6, I need 6 intervals in here. And so, yes, it makes sense. You have 7 spaces here because the 6 intervals or 6 spaces. So you need the placer for the first, second, third, fourth, all the way through the 6th one, right? So how do you figure out how big or how wide to make your x value so that you can have the right numbers? You simply take your endpoints, your b minus your a, so 1 minus a -2, and divide by the number of rectangles you want. So that would give you 1 plus 2, not 3, over 6, which is 3 over 6. That is 1/2, so 0.5. All right. Again, how did I get that? You simply take your height, the length of your x values is simply b minus a over n, the number of boxes that you have. Okay. All right. So it's b minus a over n, like so. Okay. All right. So then that means then in this particular case, I need to advance by 1/2. So -2, that's -1.5, and -1, -0.5, 0. And then 0.5, and voila, I ended at 1. So this is how I know this is perfect. Okay. All right. Again, in the interest of time, I'm going to give you the y values. That's going to help you draw this picture. And you don't need a lot of decimals because you're trying to sketch this. So actually, a lot of decimals is not going to be helpful for you. Right. So this is going to be 5.16. So 5.2. This is 4.3, 2.3, 1.3, 2. 3.8, 4.3. Okay. Using the t-table values, you're going to draw your picture, the picture of the graph, the curve, right? So right now, I want you to take the next few minutes to kind of draw the curve using this information. You're going to use this information to draw the same exact curve 3 times because they're the same graph. It's just using different types of approximation to get the area, right? So so this piece here, you are done. You're ready to go and figure out all these different approximation methods, right? So what you're going to do now is to try to draw your rectangle. But first, you remind yourself you are actually bounded. You don't want the whole thing. You only want to look from -2 to 1, right? From -2 to 1. So again, you're really looking at this area that's under the curve between -2 to 1. So again, looking at this and knowing what we know, we actually don't know much because, you know, the methods you have so far relies on you using geometry to find this area, and we don't have very good shapes here, right? The area I'm looking at, and I'm going to try to draw this very lightly because I'm going to try to use something else to show you. But this is the area we're looking at. It's this really weird curvature, right, between the curve and the x-axis, and this is the piece I'm looking for. This is the area I'm looking for. So there's no geometry that's going to really perfectly solve for this area for me, right? There's no triangle, rectangle, trapezoid that's going to fit perfectly. So this is why we need to use some rectangles to help us, okay? All right, so with the first method, that is your LRAM, is going to use the left endpoint to draw your rectangle, and you're going to draw 6 rectangles using the left side of the endpoint. So let me try to help you out with that, right? So the first rectangle is between -2 and -1.5, right? And you see, I'm going to show you where the rectangles are, but I'm not going to draw the heights yet. And the next rectangle lands here at -1. Again, exactly at all these values, right? You're at -0.5, 0, 0.5, and 1. And you'll see if you count the spaces, there are 6 spaces for 6 rectangles. Now the matter of how high to draw these rectangles. That's what the endpoints are. How high to draw my first rectangle? Well, my first rectangle is going to go all the way up to where the y value of the 2 is, -2, because that's the left side of that rectangle. I'm going to draw to the right. Okay. And then, I'm sorry, this is kind of bad. So draw to the right this way, and then come straight down, and that's my first rectangle, right? And you will see this approximation, yes, it's going to be overestimating, because if you look at that rectangle versus my actual graph, a little bit of a triangular piece on the outside that's not really a part of the area I want. So again, these are approximations. Sometimes you'll overestimate, sometimes you'll underestimate. We'll see. The next 2 points, same thing. We have this point here for, part of my height, but I need to use the left side. So from the left side, I draw across like so, and then I come straight down. So this is once again another overestimate, and that's okay. All right. Again, next rectangle, same thing, using the left side, go across, draw my height, come straight down. Okay, so far I'm always overestimating. It's going to even out. In the next piece, the left side is actually right here under. So I'm going to go across and come straight down. And you notice this one is going to be underestimating. So in a way, these over and under is okay because they're going to cancel each other out, right? This piece that's underestimating, you see it's kind of close to my overestimation on the other side. So maybe that's going to be very helpful for me, right? So same thing in my next rectangle, I'm going to use the left side, go across, and that's going to end my rectangle like so. And then the last piece, you see I need to use the left side here. This is going to be my rectangle. All right, so this is my rectangle here, and then comes straight down. And there you go, there's my LRAM. And again, you see, notice how I never use this last y value, because like I've defined it in my definition up there, the last value is not going to be used because that's the right side. I'm only using all the left endpoints, right? So what I'm going to do, my job to help estimate this, is to figure out how big these rectangles are and then add them all up. Now you will see LRAM is equal to, you will see every single rectangle here is perfectly lined up, so that every single width, every single base or height, every single base is 1/2, right? And this is a half, this is a half, this is a half, this is half, this is half. So everything is a half. So I don't really want to waste my time doing base times height plus base times height plus base times height. You can factor out all those bases and simply say, okay, 1/2, because everybody is 1/2, and then just add up all the heights. So 5.2 plus 4.3 plus 2.3 plus 1.3 plus 2 plus 3.8, right? Remember, we don't use the last one because then we never use that as my last height, okay? All right, now, and again, in the interest of time, let's go ahead and use our calculator to help us, because I don't want to spend time doing this all in our heads. So 5.2 plus 4.3 plus 2.3 plus 1.3 plus 2 plus 3.8. Check my numbers. 4.2, 4.3, 2.3, 1.3, 2, 3.8. I get 0.5 times 18.9. So my approximation for this particular area is roughly 9.45. Okay, 9.45. So that is my answer here for this particular approximation method. Okay, now let's try, what about a right endpoint? Would that give me a better estimation? I don't know, right? So let's see. So again, the next one is still the same 6 rectangles because it says n equals 6. So we still want 6 rectangles. So the division, the separation is still the same. Do you notice how I'm trying to kind of show you where my rectangles are going to lie, right? But now in the first set, I don't go to the left, I go to the right. I start from the right endpoint here, and I go towards left to finish my rectangle. And then come straight down, come straight down. So in my first case, I'm going to underestimate. Exactly opposite of what happened with my LRAM. So if it was overestimating an LRAM, it's going to underestimate an RRAM. Okay. Same thing with the next rectangle. I draw down. I take the right side and go towards the left to draw my height of the rectangle. Right. Same thing. Draw this down and then go across. There's my height. And now I'm done with my underestimating because the next piece is going to overestimate and go straight like so. Right, there's my next piece, and then next piece across, same thing, it's going to overestimate, and then lastly this piece right here. So again, just like before, we have some underestimating, some overestimating. It's not going to be perfect, but it's going to give me an idea, right? Again, if I want to, I can show you. This is the shaded area. This is the rectangle. These are the rectangle pieces that is helping me estimate this area that I really want. And again, the sum over and sum under, right? Now, some of you may notice this, that if you have more rectangles, you have more accuracy because there's less of the over versus the underestimating. So you're right. If n is bigger number, if you have the more rectangles you have, the better answer you have. Unfortunately, this is what we have right now, right? And unfortunately, you really don't want to do too many n's. If n is like, of course, if n is 100, it's awesome because that's really, really close to the actual graph itself, but that's a lot of work on us. So for now, again, for learning purposes, we keep our n relatively small. I think 10 is like the most we go. But of course, yes, there is a possibility of going infinitely big and infinitely many rectangles to get you the correct answer, right? So hint, that's kind of something we're looking for. Okay, so RRAM in this case, we're using the right endpoint, but the height is still the same. Every single one of these rectangles has a base of 0.5. So 0.5 now, but instead of starting with the first y value, which I didn't use, I'm going to start with the second y value. So it'll be 4.3 plus 2.3 plus 1.3 plus 2 plus 3.8 plus 4.3. All right, so 0.5. So what is that going to get me? Let's see. I am going to add them all up. And I should get, wow, exactly 18. So if I multiply it out, I get 9.0. All right, so you see this one's a little bit less than the other one, maybe because this one has less overlap, right? Or again, it really depends on the curvature of my graph. So then my overestimate versus the underestimation is going to be a little bit different. Okay. All right, so now I've used my t-table the way I'm supposed to. It says, one says don't use the last one says don't use the first one, which happened in both cases now. And now for a midpoint, what if I use the middle between those two endpoints to draw my rectangle? Will I get a better estimation? I think so. I think you'll get a better estimation, but you know, again, what are my values? So here is the thought. My rectangles are still going to divide up the same way. Do you see how these are your 6 spots, right? But now here's a problem. I don't want to use -2, nor do I want to use -1.5. I want to use a point right in between this point right here and figure out what its height is so I can draw across like so and draw my very first rectangle to see that, wow, this one, do you see how in this particular rectangle I have a little bit of overestimate and I have a little bit of underestimation, so they will actually cancel each other out better than it did before, right? So what is that y value? What x value gave me that y value? Was between -2 and -1.5, so -1.75. Right. Once you have the first number, the rest is easy because you're going to increase the same way as you did in the previous t-table. The previous t-table went up by 0.5, you're going to go up by 0.5 again. So negative 1.25, negative 0.75, negative 0.25, 0.25, 0.75. And again, if you check into this, you will see those are the values that will give you. You see again how I go, this is negative 1.25. I go all the way up to my graph. That's the y value, and I use that to draw across both left and right, and then come straight down to draw my rectangle. Okay, same thing, go in between, find the y value, go across, come down. Go in between, y value, come down. Go in between, y value, come down. And lastly, in between, here's my y value. Again, hopefully you'll see this approximation seems a little bit better because every single rectangle has a little bit over, a little bit under. I think that makes it a little bit of a more accuracy. And you probably can guess it should be in between the LRAM and the RRAM. Okay, so again, if you punch this graph into the calculator, you'll get these y values. You get 5.1, 3.3, 1.6, 1.4, 2.9, and 4.4. Okay, so now MRAM, although this seems a little bit weird, but MRAM here, you will see it actually does not change the horizontal distance. Your height is still the same on this one. Previous ones were all 0.5. This is also 0.5. So every single base is still 0.5, but then the only difference is your height is different. So you're going to multiply by 5.1 plus 3.3 plus 1.6 plus 1.4. Sorry, I'll zoom in, plus 2.9 plus 4.4. You will see you have 1, 2, 3, 4, 5, 6 heights because there's 6 rectangles. Okay, all right, let's see your calculator. 5.1, 3.3, 1.6, 1.4, 2.9, 4.4. Okay, that gives me 0.5 times 18.7, so that the approximation gives me an approximate area of 9.35. All right, you see my answer is between the LRAM and the RRAM, and that is going to be true all the time. Your MRAM should be an approximation that's between your LRAM and RRAM. So is MRAM the better way to go? Yes, most of the time. However, you don't always have that choice. Okay. All right. So I'm not going to spend time going over the next one because the next one is the same thing, except now we're looking at a trig function. So you're going to make your t-table using the trig function. You're going to use some approximations, right? So I'm going to post a completed version of the notes here on Canvas for you, so you can definitely double check and see if you want to practice this and see if you got the same thing. Okay, so when is this useful? Because I'm sure the thought in your mind is, if we have calculus and we have the function itself, we really don't need this LRAM, RRAM, because calculus allows us to figure out the area between the curve and the x-axis, and we're going to learn how to do that in lesson 6.4. So when is this useful? There are cases where we don't have the function, where we are only given the data points, right? So for example, in a problem like number 3 here, it says a length of a road. You and a companion are driving along a twisty stretch of dirt road in a car whose speedometer works, but the odometer is broken. So you know how fast you're going, you don't know how far you've gone. Okay. To find out how long this particular stretch of road is, you record the velocity at 10-second intervals. So every 10 seconds you record, this is how fast we're going, this is how fast we're going, this is how fast we're going. So again, do you see how in this t-table you can easily look at the fact that you have LRAM and RRAM, but there's no MRAM because you don't have a data point for the midpoint, right? So it says estimate the length of road by averaging LRAM and RRAM sums, okay? So you could, step 1 is to draw this out, and you will see, again, using the final product of what I posted on Canvas, you will see that this is going to be a very fun curve because it's really not it's not a very even road, right? So let's see, to make it easier for you, I'm going to make sure you have the right scale for this. I believe because it's going by 10-second intervals on your x-axis, you want to count each box as 10. So 10, 20, 30, 40, 50, and then you have 100, and you have 150 seconds, right? And for velocity, you can see the highest velocity you have is 44, which is awesome. then that means then if you count the boxes, if you make each box 3, which is a really weird number, but if you make each box 3, you get 3, 6, 9, 12, 15. Then 1, 2, 3, 4, 5. That makes it 30. Then 1, 2, 3, 4, 5, and that makes it 45. Okay, so I'm going to spend time to do the first one with you to show you what it should look like, right? And then you can graph the second one yourself because it's the exact same graph, right? So let's graph the data points. In terms of data points, here you start at 0, 0, and at 10 seconds you're at 44. So right here, 20 seconds you're at 15. You slow down, and then you speed up again. You're at 35. So 33, 36, 35 is right here. And at 40, you're at 30 seconds. At 50, you're at 44 again, right up here. And at 60, you're at 35, right here again. And at 70, you're at 15. And then you're at 22. So 18, 21, 22 is right here. And at 90, you're at 35 again. And then you're at 44 again. Then you're at 30. And last but not least, you're at 35. So 33, 35 right here. Okay, so those are your data points, right? And then if you really want to curve it, it's just a bunch of zigzag, bunch of curves. Okay, so we're going to use LRAM. So if I remember correctly, LRAM for me was red. Okay, we use LRAM to figure this out, figure out the area, because what the area indicates is actually distance, right? So this is how far you travel. If you look at just the first piece, right, between 0 to 10 seconds, you went as fast as 44 feet per second. So if you are looking at RM, that means you went 10 seconds, 44 feet per second, multiply that together, you went 440 feet. But that's assuming you're using the right endpoints, because that gives you the 44 feet per second, right? So if you start on the left side, we're going to start with 0. We're saying the first 10 seconds, 0. We got nothing there, okay? So that's why my first graph is going to look like this. My first rectangle is 0. It's nothing. My second rectangle is going to go from here to here, because that's using the left endpoint. And then the next rectangle is right here. And then the next rectangle is right here. And the next rectangle. And again, you can probably guess this is how I'm going to finish off the whole problem. I have to use the left side to draw my rectangle. So you notice how I always start from the left, draw my rectangle to the right, and then finish my rectangle. Draw my rectangle to the right, finish my rectangle. And you will notice that if you did this correctly, you cannot use that last endpoint. So that ends me at 120 seconds exactly. Okay, so using LRAM, you will see then that how far have you traveled? Well, each interval is 10 seconds, and then you take your speed that you are using for each of the rectangle. Now remember, you're using the left endpoint, so you're going to use the speed from the left side all the way to the one right before the last one, right? Except the last one. So 0 plus 44 plus 15 plus 35 plus 30 plus 44 plus 35 plus 15 plus 22 plus 35 plus 44 plus 30. Okay, so that will give me 10 times 349, which gives me the approximation for this stretch of road to be 3,490 feet. Okay, now again, why do we need to do the RM? Because if you recall, this may not be the best estimation, right? If you look at the previous example we were doing, an LRM and RM could be over and under. We don't know which one. So if you have two of them, you have the LRM and RM, and you average it out, you actually get a better answer, right? So spend some time drawing that second one so you can get practice on drawing the rectangle. But for the mathematical part of it, the RM is going to be 10 times everything except the first one, right? So it's going to be 44 plus 15 plus 35 plus 30 plus 44, 35, 15, 22, 35, 44, 30, and 35. And that would give me 10 times 384, which gives me an approximation 3,840 feet. Okay, so because now I have the LRAM and the RM, I don't know which one is better, but I know they're both approximation. One is usually over, one's under. Now to find the best estimation is to average these out and go 3,490 added to 3,840 and then divided by 2. So your approximation is 3,665 feet. And that is a very good approximation of how long this road is. Okay, so this is a quick idea, a quick intro on LRAM, RRAM versus MRAM. You do want to practice a little bit more. So there's another example down here for you to use if you want. And also the worksheet numbers 1, 2, and 3 that will focus on how to do this. Okay, all right, that's it, guys.